Jordan-Holder theorem. Let G be a finite group. Any two composition series of G are equivalent. Let G equals to G naught contains G1 contains so on contains Gn equals to series E, and G equals to H naught contains H1 contains so on contains Hm equals to series E be the two composition series of G. This is equation 1 and this is equation 2. So we shall construct the two composition series equivalent respectively to 1 and 2, which are themselves equivalent, since for the composition series the relation of being equivalent is an A equivalence relations. This will prove the theorem. We shall consider the two cases. Case 1, G1 equals to H1. Since order of G1 is less than order of G, by the induction on order of G, the two composition series G1 contains G2 contains so on contains Gn equal to series E, and G1 equals to H1 contains H2 and so on contains Hm equals to E are equivalent. This shows that 1 and 2 are the equivalent. Now case second, G1 not equals to H1. Now G1 into H1 is a normal subgroup of G containing both G1 and H1, and G1 H1 equals to G, since otherwise G1 H1 equals to G1 equals to H1. Moreover, G over G1 equals to G1 H1 upon G congruent to H1 upon G1 intersection H1 and congruent to H1 upon K2, where K2 equals to G1 intersection H1. Similarly, G1 upon H1 equals to G1 into H1 upon H1 congruent to G1 upon K2. Since G over G1 and G over H1 are simple, the group G1 over K2 and H1 over K2 are also simple. Now let us consider the composition series K2 wise. K2 contains K3 and contains so on contains Ki equal to series E. Then the following series are the both composition series. G1 contains G contains G1 contains K2 contains so on contains Ki equals to series E equation 3, and G contains H1 contains K2 contains so on contains Ki equals to series E equation 4. Now 1 and 3 are the equivalent by the case 1, and similarly 2 and 4 are also equivalent. Now 3 and 4 are themselves equivalent because the quotients in these cases are G upon G1, G upon K2, K2 upon K3, and Ki minus 1 upon Ki, G upon H1, H1 upon K2, and K2 upon K3, and Ki minus 1 upon Ki. And the first two quotients are the isomorphic in the reverse order. This shows that 1 and 2 are the equivalent.